the third lecture on Euler-Lagrange mechanics. In the first class, we have derived the Euler-Lagrange equation from the Hamilton's principle of least action, and in the second class, we have applied the theory to simple problems belonging to conservative holonomic class. In this class, we shall explore some of the properties of the Euler-Lagrange equation. Namely, today we shall discuss the gauge function of Euler-Lagrange, or gauge function for Euler-Lagrange equation, and we shall also establish the invariance of Euler-Lagrange equation and Galilean Transformation. So first is the gauge function. Gauge function for Euler-Lagrange equation. Henceforth onward, we shall abbreviate Euler-Lagrange equation as ELE. So, we have a Lagrangian L which satisfies the Euler-Lagrange equation ddt of del L del Q K dot minus del L del Q K is equal to 0. Now, we change the Lagrangian L to L prime, which is equal to L plus df dt. Our aim is to show that this L prime also satisfies the Euler-Lagrange equation, where f is a function of generalized coordinates and of time. It does not depend on generalized velocities, and we are to show that ddt of del L prime del Q K dot minus del L prime del Q K is equal to 0. In which case the f is called the gauge function. In electrodynamics, we have seen that if we change the scalar potential phi to phi prime, where phi prime is equal to phi plus c, then both this gives phi prime gives field electric field as this, and while phi gives the field this, and we know that E prime is equal to E, and we said that electrostatic potential has an arbitrariness to the constant of an additive constant, that if we add some constant to the electrostatic potential, that field doesn't change. Electrostatic field doesn't change. On the case of magnetic vector potential, if we change A to A prime, where A prime is A plus gradient of chi, where chi is any well-behaved scalar point function, then we know that B prime is equal to curl of A prime, and B is equal to curl of A, and we know that B prime is equal to B, and we say that this is the gauge property of vector potential. That is vector potential, if we add some gradient to the vector potential, then the resulting field, magnetic field, remains unaltered. Here the gauge function is similar. If we add this term to L, then if L satisfies Euler-Lagrange equation, L prime also satisfies Euler-Lagrange equation. In other words, df dt itself satisfies Euler-Lagrange equation. To prove this, we shall follow this technique. ddt of del L prime del Q K dot, where capital X we define a quantity, minus del L prime del Q K. This is equal to ddt del L Q K prime For L prime, we write L plus df dt minus del del qk L minus L plus df dt. The first term is ddt of del L del Q K dot minus del L del Q K, which by this equation, by this relation is 0. The second term is ddt of del Q K dot, or acting on, df dt minus del del Q K operating on df dt. Since this part is 0, only this term survives, so we have ddt operating on and we change and this term. First is ddt of del del q k dot operating on df dt, which is written as del f del t plus summation over I is equal to 1 to n del f del qi dot. Here, since f is this, we can write df dt, the total derivative of f is del f del t plus summation over I, all the degrees of freedom, del f del qi dot, which is written over here. And for this term, we just interchange the order of differentiation. So this is ddt of del f del qk. Now coming to this term, ddt, this first operates on this, so we have del del qk dot del f del t plus summation over I is equal to 1 to n. First, this operates on this, in which case we have q, this is qi dot del del qk dot operating on del f del qi plus this operates on this, so del f del qi del qi dot del qk dot, this is the end of second bracket, end of third bracket, then ddt of del f del qk. Now you see that the gauge function f that we have introduced is a function of generalized coordinates and time. So if we interchange the order of differentiation here and we interchange the order of differentiation over here, we have already done once such transformation here. So we get from the first term ddt of del del t operating on del qk dot plus summation over I is equal to 1 to n qi dot del del qi del f del qk dot plus del f del qi, and this part is delta ik, because we can write it as del qi del qk minus ddt of del f del qk. Here we have used del qi dot del qa dot is equal to del qi del qk is equal to delta ik. So this part is delta ik. And this part is 0 because f is not a function of generalized velocity. So these two part goes, only this part survives. And we have ddt of summation over I del f del qi del f del qi delta ik minus ddt of del f del qk. If we carry out this sum over I, then only that term contributes for which I is equal to k, in which case this is equal to ddt of del f del qk minus ddt of del f del qk, which is equal to 0. So we see that if we add the total derivative of a function f, of a quantity f, which is a function of generalized coordinates and time to the Lagrangian, then Euler-Lagrange equation remains invariant, and the function f is called the gauge function. So if the total derivative of a quantity which is a function of generalized coordinates and time, called the gauge function f, called the gauge function. Note that f is gauge function, not dft. There is added to the Lagrangian, added to Lagrangian L. The Euler-Lagrange equation remains invariant. That is, it does not change itself. In other words, that is the df dt itself satisfies Euler-Lagrange equation. That is, df dt itself satisfies Euler-Lagrange equation. This is the one very important concept of concept in connection with Euler-Lagrange equation, which we shall use immediately to prove that Euler-Lagrange equation remains invariant under Galilean transformation. This property will be used several times in our course of discussion of Lagrangian mechanics. So this f is the gauge function, and df dt itself satisfies Euler-Lagrange equation, provided that f doesn't have any dependence on generalized velocities. Now, the second topic that we shall take off in this case is that we shall show that Euler-Lagrange equation is invariant under Galilean transformation. First, we want to what is a Galilean transformation? Before going to speak of Galilean transformation, let us first say what do we mean by inertial frame of reference. So our topic is Euler-Lagrange equation is invariant under Galilean transformation. What is an inertial frame? An inertial frame, as per Newton's second law, is as per Newton's first law of mechanics is one in which a particle not acted upon by any force is has no acceleration. That is, acceleration A is equal to 0 if F is equal to 0. The coordinate, the reference frame in which this property holds is called an inertial frame. An inertial frame is one which has no acceleration. On the other hand, if we consider the accelerating coordinate system as, for example, rotating coordinate system, then this condition does not is not obeyed, and we see that some extra force arises which are called pseudo force or fictitious force. It is to be kept in mind that pseudo force arises singly, not in pair. As per Newton's third law, force should arise in pair. This is another reason of saying this force as pseudo force. We consider an inertial frame or a frame and fixed in lab, and it has an origin O, and this frame is called S frame. We have another frame which is moving with respect to S frame, and this is the prime frame having origin at it has its origin at O prime at a particular instant. The position vector of O prime with respect to O is R0, and let us consider a particle whose position vector with S prime is Ri. This is the particle of mass mi, and the position vector of the same particle with respect to S prime is Ri prime. Obviously, from the vector relation we have R0 plus Ri prime. This leads to velocities. This is the position in S prime, position of the particle mi in S prime. This is in S prime prime, and this is the coordinate of the origin of S prime prime with respect to S prime. This gives you velocity v in S prime is equal to velocity of the S prime plus velocity of the particle as viewed in prime prime. And this also further gives that acceleration of the particle in S prime is equal to acceleration of the coordinate system S prime plus acceleration as seen in this frame. You see that if A0 is not 0, then even AI is 0, AI prime is not 0. For Galilean transformation, this is 0 for Galilean transformation. Provided this is an inertial frame. Then this is the relation. So Galilean transformation is the transformation which relates between two inertial frames in classical mechanics. And this is a constant vector. So the Galilean transformation is this one. When viewed in S prime, we express the Lagrangian in terms of Lagrangian in terms of kinetic energy and potential energy, where the quantities are expressed in terms of the Ri dots and T. And when viewed in this frame, S prime frame, we write L prime. It is the kinetic energy in prime frame minus the potential energy in V prime frame. If we say the zero level of potential is the same in both the frames, then V and V prime are the same. Only thing is that when we express, we write V, we write the V as a function of Ri's. And when we write V prime, we write it in terms of Ri primes. So the kinetic energy part, our aim is to set up a relation between L prime and L, where these positions and velocities are related via Galilean transformation. So this T prime is half mi sum over I is equal to n vi prime square minus v prime. We write this vi prime as v minus v0. mi vi minus v0 dot vi minus v0 minus v. Here we write v because we have written every quantities in terms of those relating to S term. That's why we have written v. The first term is half summation over mi vi square, which is nothing but the kinetic energy T in S prime minus potential energy V plus summation over I is equal to 1 to n mi half v0 square minus v0 dot vi. We can rewrite this part as T, the Lagrangian in S prime plus ddt of some quantity mi half v0 square t. You note that for Galilean transformation, v0, the vector v0 is constant, so its magnitude is also a constant, and we write it as v0 dot ri. When ddt operates on this, the v0, since v0 is a constant vector, it doesn't operate on it. It operates on this, and this gives you v velocity. So we have L plus df dt, where f is a function of ri's and t is equal to summation over I is equal to 1 to n mi half v0 square t minus v0 dot ri. Since v0 is a constant, it is a function of r and t, ri's and t only. So it is a gauge function for the Lagrangian, and that's why this L prime also satisfies the Euler-Lagrange equation. So we see that the Euler-Lagrange equation is invariant under Galilean transformation. Thus we conclude that Euler-Lagrange equation is invariant under Galilean transformation as if f as given by this is a gauge function. Gauge function for the Lagrangian equation. So in this class we have proved two important properties of the Euler-Lagrange equation. Firstly, we have proved that Euler-Lagrange equation remains invariant if we add the total derivative of a function f, which is a function of generalized coordinates in time, to the original Lagrangian. So the resulting Lagrangian also satisfies the same Euler-Lagrange equation. In other words, the f is called the gauge function, and df dt itself satisfies the Euler-Lagrange equation. Secondly, we have used this property, that the property of gauge function, to prove that the Euler-Lagrange equation is invariant under a Galilean transformation. A Galilean transformation is one which connects the space variable between two coordinate systems, both of which are inertial. That is, there is no acceleration between the coordinate system, and each of the coordinate systems are inertial ones, and time is same in both the coordinate system. So this is the Galilean transformation, and Euler-Lagrange equation is the invariant equation.